We're talking about tangents today, so this is going to be an introduction to circles. Spend about a week, maybe 6 days on circles, and then we'll get into probability. Spend about maybe 3-4 days on that, and then a couple days in preparation for the EOC. So today's 12.1 is tangent. The word tangent, okay, has been used already in this course for opposite over adjacent. It was a ratio, correct? And right triangles. We're going to use the word again to define a certain type of segment or line. But what I need you to understand is the usage of this word again is done on purpose. Okay, there's a relationship, there's a link between what we did in chapter 7 to what we're doing now. Okay, I'm not going to show you that link right now. Maybe if we have time down the road, I will. But it's the fact of how triangles and circles do have connections. They have links between one another. So when we see a tangent here, it's not a completely different thing. Okay, it is still a ratio of opposite over adjacent, but now we're using this word to define a particular segment. Okay, so I'll give you guys a minute to write this down. Okay, 2 vocabulary words and a theorem. All right, so as you're writing, let's kind of talk about these. A tangent to a circle. So we're going to talk about a tangent to a circle, but this word tangent is, and the way that we describe it, it says is a line in the plane of the circle that intersects the circle in exactly one point. We can actually interchange that word circle with other shapes eventually. Okay, maybe we want to talk about an ellipse. You guys know what an ellipse is? Okay, so it's like an oval, right? Okay, we can do this with an ellipse. We have tangents to ellipses. We can actually have tangents to parabolas. Okay, and other curves in the XY plane that we create algebraically. But for our class right now, we're going to primarily talk about it with circles. But this vocabulary word becomes something that we use in other courses throughout high school that will come back and be discussed again. But they probably won't describe what it is. They'll just say, hey, this is a tangent to the sine curve or a tangent to this parabola or something like that. Okay? But it's a tangent, just kind of holistically, is a line or a portion of a line that touches a curve. Now, for us, that curve is going to be a circle at one and only one point.
Being honest, when would we use this? Like, I'm not joking.
So like a tangent line, so last class I asked this as well. If I take my keys here and I start, what shape am I making?
Get over here. Oh, I don't do that.
Okay, I'm making a circle. So I want to kind of let go of them, but I want to. So if I let go of them, that path that my keys took, okay, that path, what is that path? It's the tangent line. The tangent to the circle that I was creating when I was rotating that. Thank you.
What does that prove?
Huh? With circular motion, there's a lot of things with circular motion that we're interested in regards to that tangent line. There's a lot of high-level math with like surfaces and finding tangent lines to surfaces that is beneficial. If you've ever been on a roller coaster, let's say you're on a roller coaster and you're going down a curve and you were just to fly off that roller coaster, you're going to take that tangent line to that curve. If you're last class asked this, so I've got this kind of created here. So that is a tangent line to that's called the sine curve. Okay. Now, the tangent curve segment, so the tangent segment here to that curve is the idea. Let's say that is a windy road. Put yourself in like a bird's eye view, and you're looking down on a windy road. If that windy road, if you lost control on one of those curves, your car is going to take the tangent line to that curve at the point in which you lost control. Okay. So now, when people go investigate wrecks and things like that, where there are no witnesses, maybe they do this kind of math to see, okay, this is how fast this person was traveling, all that kind of stuff.
They do that with skid marks?
Yep. And so this math, it would be a part of that. Okay, so those skid marks is creating friction, right? So there's that dynamic that's occurring as well. But another reason in the calculus aspect, we're interested in finding the slopes of certain equations, the slopes of certain curves. Now we know a slope for a line is always the same, right? No matter where you're at on the line, the slope is always the slope of the line. So if it's 2/3 between any 2 points, then take any other 2 points on that line, it's still going to be 2/3, right? Well, the slope on a curve, a parabola, or this is called a sinusoidal. It's called a sine curve. It's the same sign that we've been using in Chapter 7. If we graph that and look at it this way, the slope of this curve is changing all the time. It is not constant. It's variable, okay? And it depends on where the point of tangency is that I'm interested in finding the slope of. So if I want to know what the slope of this curve is at, let's say, x being 4, I would come over here, okay? And now the slope of that black segment is going to be the slope of the blue curve at 4. Does that make sense? But the slope at 4 on that blue curve is different than what it is when we're at 5. Okay? Now there are things, costs and profits and stuff like that. We can get into all kinds of things of why I want to know what that slope is. In calculus, that's called a derivative. Okay? And it allows us to use calculus to explain a lot of real-life situations. Tangent lines are very important to us, and the idea of tangent lines is very important to us for a lot of higher level math and higher level physics. Okay, touching one point or touching a circle at one point and only one point is the idea of a tangent to a circle. The point in which the circle and a line touch, or the point that they have in common, is called the point of tangency. Okay. When we look at tangent lines, it's important to make the distinction that we have to be dealing with lines that are in the same plane. So that line that I just put in there, this red line there, that is not considered a tangent line. Even though it touches one time, it's not in the same plane. Does it make sense? Okay. A lot of times we might refer to that as maybe the orthogonal line, or the line that is orthogonal to the circle. Or another word for orthogonal is the word normal. We might say that line is normal to this circle. Okay. We just won't use the word perpendicular. Or normal or orthogonal, usually when we use it, we're thinking there's a perpendicular aspect. But we would not use the word tangent. Yes?
That red line would be if you're going like this and it just flew right at me, right?
Yeah, so if I'm going like this, it'd be every line that is coming through my keys towards you, perpendicular to my keys.
Can you please just do the get over here?
No. Okay, so this is an example of a tangent line. So I've got just a couple things working here. So that would be the tangent line. As I move C is the point of tangency. Okay, so those are all examples. Those are the infinite tangent lines that we could create. Now, it doesn't necessarily have to be just a line. It could be any portion of that line, so it could be a ray. And that ray could actually start at the point of tangency. Does that make sense? Okay. It could be, like I said, any portion of that line, so it could be a segment. Segment could be, we usually call it a tangent segment. Do it this way. So, okay, that is still a tangent segment. Is that tangent? No. So if I'm dealing with a ray or a segment, we still need to make sure that it actually touches the circle one time. Okay. Now, if I were to continue that E to F segment as a line, obviously it becomes tangent, but that segment would not be tangent. So, everybody? So those are the ways of viewing a tangent line. And I'll give you some, when we get to it later, I'll give you some other applications of tangent lines in real life. You saw some pictures that maybe I just closed out that might be real life situations.
Yeah.
Okay, so the key thing that I want to talk about today, and right now I've only got this thing up here, but converse is true as well. But it says if a line is tangent to a circle, then it is perpendicular to the radius of the circle at the point of tangency. Okay. So when we look here, you see this line right here, this segment, which is this blue segment is a radius, correct? No matter how big my circle is, no matter where I have my point of tangency, do you see that green angle always being a right angle? Yeah. Okay. So at the point of tangency, the radius is always perpendicular to the tangent line. I said the converse of that is true as well. So the converse is kind of this idea. If I look at those two segments, the orange one and the blue one, and I'm able to find out that at C there's a right angle, and then what's that tell me the orange one is? If I just look at this and I don't know any angles, okay? So let's do something like this. Let's say, let me hide this line real quick. All right, so you see that angle right there is 60.3, right? And it goes from A to C to Q, okay? Now, that is not a tangent. Anybody know what that line is? Chord. Okay, the segment C to Q is a chord. But the line is a, do we know what the entire line is called? A bigger chord. It's called a secant, okay? Now, we've seen secant before in trigonometry. It's the reciprocal of cosine, if you remember. And there's a direct link between why it's called a secant here and why it's called a secant in trigonometry. But here's the idea. Because that angle is not 60, or because that angle is 60.3, we know that this line here is not, so that purple line is not a tangent, right? But as I move Q, let's see here if I can make this. Okay, so as I move Q, okay, what is happening to that angle?
It's going closer to 90.
Getting closer and closer to 90. And when it is 90, Q, now it's because I'm using, in order to create this line, I need these 2 points, but kind of visualize it. Okay, when it gets to 90, this line here is what shows up. Does that make sense? Okay. So let's see here. Kind of cheat here to show this. What is that angle? Alpha? Alpha equals 90. All right, so as I move that, still didn't show up. Why didn't it show up? Alpha equals 90. Okay. Let's try and get that to show that line being defined when that does equal 90. But the idea, guys, is that has to be a 90-degree angle in order for us to have a tangent. So what I'm trying to get at is the converse here of this theorem is appropriate. It does become true. Okay, so they're going to ask us to do some practice questions with this concept. Now, what they usually do then is to get you to use this concept is to ask a question about something that we already know in the past. Okay? For instance, here, they're essentially asking you, do you know how many degrees there are in a quadrilateral? Because they're asking you to find x degrees, right? How many degrees are there in a quadrilateral?
I want to say 360.
You are right when you say 360. Remember the formula is n minus 2 times 180, right? N being the number of sides. So if I look at this shape right here, if we look at that shape right there, it is a quadrilateral, right? Okay. So we have 360 degrees in those 4 angles. Now they're asking me for x. So if I'm able to find x, I would have to know either the total and then 3 other angle measurements, right? Well, fit me in regards to getting the other angle measurements.
That's how I would go about it if I didn't know it.
What kind of segment is M to L?
That's a tangent.
It's a tangent. So if M to L is a tangent, what's O to L?
Oh, that's a right angle.
So that's a right angle. Do you see how they're telling you now, based off of that last theorem, it's telling you 2 of the 2 of the other 3 angles that are not x in that problem, right? So now if you've got 3 angles and you know the total, shouldn't you be able to come up with this last one?
Yeah.
So 90 plus 90 is 180, right? Plus 117. Subtract that from 360. Should be 63 degrees, right? Does that make sense? So this question is obviously, it's using something from, I think it was chapter 5, that n minus 2 times 180, or 360 degrees in a quadrilateral, to allow us to apply the tangent rule with the radius. And again, a 90-degree angle there. Okay? They often ask those types of questions on the course exam in regards to a tangent line. If they're going to mention a tangent line on that test, they usually do it in regards to trying to tell you somehow there's a right angle somewhere. Okay? Same thing happens here. Okay? Says ED is a tangent to circle O.
Whoa.
Okay? So what kind of triangle then do we have there, that black triangle? It's a right triangle. How many degrees do you know right now for that right triangle? You know 2 measurements, and they total 128 degrees, don't they? Yeah. 90 plus 38. So angle D is a 90-degree angle. That's the theorem that we just talked about. A radius, which is OD, is always perpendicular to the tangent line. So X, you said, had to be 52. Is that something we can do?
Yeah.
All right. So the next question I want to talk about is actually applying. Actually, do one before that. So do one more of these that incorporates that concept, knowing that CB, and usually what they'll do, guys, is they won't. It's pretty obvious what to do here when that right triangle is there, or right angle is there. They'll do something like this. They'll tell you AB is a tangent. Or they'll say, assume that the lines that look like they're a tangent are tangent. So AB is a tangent line. CB is a radius. So then you know that is a right triangle, correct? If that's a right triangle, what theorem, right, the Pythagorean theorem is going to allow you to work through here and figure out what x is. Okay? Because now it just breaks it down. By knowing that fact, it just breaks it down to having a right triangle. So, what is one leg for your right triangle here? 12. So square that. What's the other leg? X. What's your hypotenuse? Okay. And we'll square that, right? Now this is the number one.
I think people do wrong. They square.
Yes.
Square the X.
Yes. Okay. Every ACT that you have probably ever encountered or will encounter will probably somehow address this to get people to make this mistake. Okay. Now it might not be in regards to using tangent lines or something, but the algebra will be presented this way: as x plus 8 squared. And the number one thing that people do is they write x squared plus 64, and then they go on. Does that make sense? Why is that wrong?
Because you got to foil.
Okay, so if I FOIL, what I'm missing is O and I right now, correct? So x plus 8 squared is actually this. X squared is first times first. 64 is last times last. I'm missing O and I, right? Which gives me 16x. Now, what happens with this x squared here and this x squared there? Okay, so I'm left with 144 is equal to 16x plus 64. Gives you 80 is equal to 16x. What's x got to be then? 5. Okay. So now here's my question. And here all they ask is what's the radius. Could I have changed this question and said what's the area? And go one step further, right? What's the area of that circle then?
I don't want to do it. It's 5.
25 pi.
What?
Pi r squared. R is 5 squared, you get 25. Okay. All right, you could find the area of the triangle. They might even ask you to figure out that area. Could I take the area of the triangle minus the sector there?
No.
Okay. Now, in order to do that, I would definitely have to know maybe that angle right there or something like that. But there are so many different things that they can do to get you to use this tangent property. All right, so this is a question then that targets the converse. This question here targets the converse. They want you to explain whether ML is a tangent or not. Okay? If it is a tangent, what should angle L be?
It should be a right angle.
It should be a right angle. Okay, that is provided that you do have a tangent line here.
It is.
So what theorem? Okay, so the Pythagorean theorem. If the Pythagorean theorem with these numbers is true, then that is a right angle, and then that is a tangent. Does that make sense?
It is true.
Okay. So what's the leg or a leg? 7. What is another leg? Okay, and that makes the hypotenuse.
6.
Okay,
I
so
was going to say 625.
7 squared is 49, 24 squared is 576, and 25 squared is 625. Because when you add the left-hand side, you get 625 equals 625. That is the converse of the Pythagorean theorem, which says if you satisfy the Pythagorean theorem with the values that you have, then that means that the angle is a right angle. So if that angle is a right angle, then that line is a tangent, right? ML is a tangent. Okay? Where? Oh, it says the word true. What if this number here was bigger than this sum?
It'd be a cube? No, it'd be obtuse.
If c squared is bigger than a squared plus b squared, then it's obtuse. If it was less than, it would be acute. Okay? Not like you. There is not a hideous angle. All right, this question, guys. This one, and this is in your homework. Now, they don't necessarily give you 60. I don't think in your homework. It might give you like 38 or something like that. Everybody's a little bit different.
That's 120. That's not a...
The one thing I need you to understand is that this here, I think, is in a bad spot, and it's going to be kind of visually confusing in your homework, just because for some reason in Math Excel they want to make their pictures very, very tiny. I don't know why they do that. But X is that angle down there. In your homework, people a lot of times have thought X to be that angle. So just be careful, because they've just kind of put it out here, hanging out in the middle, right? But it is that bottom right angle. Okay? So now, when I go through this problem, I need to figure out what X is. And there's a couple different... What is that angle right there? That angle is 90. So we know that angle is 90, right? Okay. That's the radius intersecting a tangent line, right? Now, this angle here then is 60. All right, so this is, because it's 60, this is kind of a unique way of doing this problem. So we'll do this again with a different number other than 60. But if that's 60, what kind of triangle is this triangle here on the inside? Equilateral. Initially, it's isosceles, right? But an isosceles triangle with one 60-degree angle is actually an isosceles triangle with three 60-degree angles, making it equilateral and equiangular, right? So, this angle here, 60 degrees, right? All right, so if my overall goal is to find out what x is, kind of eliminate all this other garbage in the picture. If this is 60, you said at the beginning that was 90, right? This has to be 30.
So whenever you get a question, look at that as 30. Yeah.
No. Because what if that angle 60 is an arbitrary value, right? Let's say that angle ends up being 63. Okay? If that's 63, are all the angles, like in the last one, all the angles were 60, right? But that one's 63. Are they all 63? Okay, so what's 63 plus 63 plus 63? 189. Can you have 189 degrees in a triangle? No. But if this is isosceles, what does this angle here have to be?
63.
63. And if that's 60, now you got 126, right? You have 126 right here. Okay, you can do it that way. If I look at this triangle, this triangle here first on the inside, you have 126 degrees used so far, right? This one? Because I know that this is isosceles based off of that side and that side, so the angles opposite those have to be the congruent angles. The base angles of an isosceles triangle are congruent. So the red ones are the base angles. Chapter 4. So if this is 126 degrees, how big does this blue angle have to be? 54. So if that's 54, kind of go back through that's 54. You know this angle here is 90, so that's 144, right? What's this one here got to be? 36, correct? Okay. Now, what Alex was doing, you found this angle here to be 63, right?
Yeah.
Okay. Then you said, well, this angle here is 117. Is that okay with everybody? If this was 63, not 60. If that was 63, doesn't this angle here have to be 27? So now he was looking at this triangle here, and he's saying, I've got 27, I've got 117, 27 plus 117, does that give me?
144.
144 again? Doesn't that have to be 36? Okay. Some people might look at it this way. We said that was 63, right? Is 63, 27, and that angle there, is 63 an exterior angle for those two remote interior? Okay, so 27 plus what will give me 63? 36 again. Okay. So there's a lot of different geometry existing inside that question that could allow you to solve for x. But if we don't know what this angle here is being described as being 90 with the tangent and radius, we can't do any of that problem, right? Any technique.
I thought it 89 degrees. Yeah, that is not triangle. Yeah, what? 189 in the triangle. I thought it was 189 less degrees.
All right, so I'll look at this picture. All right, so what they talk about next, and I'll give you a minute to write it down here in a moment, but they say you start with a point that is on the outside of your circle. So I, up there to the right, is outside my circle, right? Okay. If we were to draw or construct from I the two tangents, that tangent line and that tangent line to that circle. Does that make sense? So every point I is going to have, from any point I, you can draw two tangents to any circle. Does that make sense? Okay. Now, if I just focus on from I to the point of tangency, those two distances right there, those two orange distances, what do you think the argument that you're going to make is about those two orange distances? Why? What is that segment called? A radius. What is that segment called? A radius. Are they congruent to one another? All the time, right? That segment is what for both of those triangles? It's the hypotenuse. It's opposite the right angle in both those triangles, right? Is it the same segment in both triangles?
Yeah.
So is it congruent to itself?
Yeah.
So do you have a hypotenuse in the top triangle congruent to the hypotenuse in the bottom triangle?
Yeah.
If the radii are legs of those triangles, you have a leg congruent to a leg.
Yeah.
So those two triangles congruent by hypotenuse leg.
Yeah.
So then by what logic is this distance there the same as that distance? No, hypotenuse leg is a statement like side, angle, side. So side, angle, side, 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 angle, side, angle, hypotenuse leg, all of those are ways of first determining the triangles to be congruent. And then what is always the next step?
Congruent parts of congruent triangle, or congruent parts of, yeah.
Corresponding parts, so matching parts, okay, of congruent triangles are congruent. So CP, CTC, okay? So, and that's, we've been kind of away from proofs for a while, but everything that we do, guys, every one of these little theorems that we come up with, I'm not saying every single one, but a lot of them have a triangle congruency aspect to them that allows them to exist in the manner that they do. Okay? So no matter where we move point I on the outside of my circle, are those distances the same? Yeah. Okay? Now the next thing we start doing is this type of thing. Okay? So I just created O and P, right? O and P were just some arbitrary points outside the circle, and I drew those tangents. Okay? What does that circle end up being called for that triangle? The inscribed circle. Okay? Now, we've been talking about inscribed and circumscribed things for a while, right? And I've always added the feature, the statement, that to be inscribed, you need to have the segments of the polygon touching your circle each one time, right? How can I now clean that up a little bit? Tangent to the circle, okay? So now instead of having to say that every single segment of my polygon needs to touch my circle one time, I just say that every segment of my polygon needs to be tangent to my circle. And that cleans up the definition for inscribed a little bit better, okay? So to be an inscribed circle, and it doesn't just have to be a triangle, could be any other shape. So we've seen these shapes before here, okay? But in order for those black circles to be inscribed, then each segment of the red polygon needs to be tangent to the black circle. If not, it's not inscribed, okay? We've talked then about the polygon. If you want to reference it, it is called the circumscribed polygon.
So I'm guessing you're going to have a picture of that and you're going to say, is it a inscribed circle?
I might ask that kind of stuff, yes. And my whole reason of going through the vocabulary with you and having a lot of vocabulary in this course is, one, so we have conversations. But two, when you get to the end of the course exam, they're going to use them. If we haven't been exposed to them, we're not going to have a clue, right? If you can't read the directions or try to analyze what they're asking you to do because you don't know the vocabulary, it's a very limited chance that you're going to be successful in that problem. Right?
Yeah.
Okay. Okay, so there's a couple other vocabulary words here that I want to get to. But I think it makes sense to show a picture first. You have, let's just view these two circles as just like two CDs.
Big brother, little brother.
Two CDs, same or of different sizes, right? Maybe maybe two different records. Okay, you guys know what records are?
Yeah.
Okay.
We know.
So we got two different sizes of it. Can you envision or think about taking a line that would be tangent to the small one and drawing it so that it is also tangent to the big one?
No.
You can't visualize that line? Okay. So the road is always what we call a common tangent to your wheels on your car. Does that make sense?
Yeah.
Okay. Now that's a common, what we call external tangent. Okay. Because that tangent is on the outside of both your circles, right? Or both circles are on the same side of the tangent line. So it's a common external tangent. Yes?
Wouldn't that have to be level then, though, for them both have 90-degree angles?
Nope. So if we go, where's my perpendicular? Here we go. To kind of, and the idea, if I wish I could like maybe grab the whiteboard up there and rotate the whiteboard, but if I were to rotate the whiteboard, I can always take, if this is the road, I should always be able to take it and make it horizontal. And now you can see if that road is horizontal and our radii are vertical, you do get those right angles. Okay? There's something wrong with you. The other idea is that you can have a tangent line there. Okay? So you always, with two separate circles, you're always going to have two common external tangents. Okay? So are they ready? Now, if I look at those, let's just highlight real quick. That distance there, that distance there, and then that distance, and that distance. If I were to just look at that shape that I just traced out, what does that look like?
That looks like a tank tread.
So tank treads, okay. Okay.
It looks
I agree with that.
like in the ice cream machine.
Oh, it looks like the belt on it. Yeah.
Okay. So belt on an engine, okay, serpentine belt on an engine, the belt on, or the rope on pulleys. Anybody ride a bike? That looks like the gear set up on your bike, okay, and a chain. So the chain would be the blue segment, right? Or the belt on the pulleys would be the blue segment. Now the length of the tangent lines and the arc length of those circles is going to be a component to finding the chain on or the chain length on a bike. Does that make sense?
Yeah.
Okay. So those of you that have opened the hood on your car, you would see this type of stuff going on the inside of your car, right? Okay. Those belts there are tangent to certain circles, right? Okay. And that math and that knowledge is all a component to finding the correct length of the belt that we need for this maybe setup of the engine. Okay.
My car doesn't have an engine. Okay, not that exact engine.
Would you agree that I could put a line that is tangent to the circles that way?
Yeah.
Okay. Can you find another one?
Yeah. Ooh.
Okay. So those are still common tangents, but they, and this is the way that we define it, those two tangents intersect that line right there that connects the centers. Because those two tangents intersect that dotted line, we call those internal tangents. Okay? The way I like to visualize it, would you agree that they intersect kind of on the interior kind of area between those two circles? Or maybe you could think about it as it's an internal tangent if one circle is on one side of the line and the other is on the other side of the line. Does that make sense? An external tangent, they are both on the same side of the line, right? Internal, they're on alternating sides. Okay, now let's do this. What happens if I start taking this circle here and getting it closer and closer Okay, so now your two internal tangents become one still internal tangent. Okay, but when that happens, think about these two things being CDs, these two circles being CDs or records. How many times are those circles touching? One time. So now what we can say those circles are to one another? If they touch one time.
They love each other.
Touching, what's the word for touching one time?
Adjacent. Sensitive.
What kind of line is that?
Tangent.
Tangent, because the tangent touches the circles one time, right?
To each other.
So the circles are now said to be tangent to one another because they have one common internal tangent. Now the circles, because they are on the outside of one another, they're considered to be called externally tangent circles. Okay? How is that? They're externally tangent. View it this way. Let's say I look at these two. Okay, still have two tangents, right? They're external tangents, right? Still have two, still have two, still have two. Now, they're becoming one, and it gets right there, right? Now you have one circle inside the other, right? So they're internal circles. How many times do those internal circles touch? Once. So we call those internally tangent circles. Okay? So you're going to have externally tangent circles where they're not overlapping, or we're going to have internally tangent circles where they are overlapping. Can I have... Do those have common tangents? No, because if I did, think about this. Let's look at just a tangent for the inside one. All right, if I got a tangent for that line, that circle right there, how many times does it intersect the outside circle?
Twice.
Twice. So it's not a tangent for the outside circle. What about if I look at the tangent for the outside circle right there, H? How many times does that intersect the inside circle? None. So it's not a tangent for the inside circle, right? So they're not common, they're not shared. Okay? So the last 4 slides, guys, of that PowerPoint, my hope so you download it, and you go through, and we've got these top ones are, I think this slide is just talking about what common tangents are. Yes, common tangents, then the common internal tangent, the common external tangent, and then tangent circles. So if you want to write that down and get that in your notes, please do that. But my hopes are that explanation is good enough for us. I've opened up a couple assignments, guys. First of all, the thing that is most important right now, reading.